Good evening, sir.
Yes, good evening.
Sir, you can start, sir.
Okay, ma'am. Thank you so much. Good evening, students. Last class, we started our discussion on alternating current. And in this class also, we are going to continue our discussion on various concepts in alternating current. Now, I will be sharing the whiteboard with you. Are you able to see the whiteboard, students? Are you able to see the whiteboard? Students, are you able to see the whiteboard? Can you hear me? Am I audible to you?
Yes, sir.
Okay. Can you see the whiteboard, students?
Yes, sir.
Okay. Thank you so much for your response. And last class we discussed something regarding the alternating current, and we discussed regarding the average value or mean value of alternating current. And in this class, I will be starting my discussion from root mean square value. Okay, root mean square, that is RMS, otherwise called effective value. Okay, of alternating current, that is abbreviated as AC. Okay, root mean square or effective value, RMS or effective value of AC. Okay, so what is the meaning of this root mean square or RMS value or effective value? What is the meaning of this? Actually, you can understand the meaning from the technical term itself. Root mean square. Okay, root mean square. That means you need to consider the instantaneous values of the currents in an AC circuit. Okay, not only current, it can also be voltage. Okay, be it graph between voltage or time, or voltage versus time, or it can also be a graph of current versus time. In both these cases of alternating current, you can choose the instantaneous values from the graph. You can choose, for example, five instantaneous values of current or voltage from the graph, and then you need to square that. Okay, you need to square that. So after squaring those values, you need to take the arithmetic mean or average of the instantaneous values, and then you need to take the square root. Okay, so the arithmetic operation should be considered from this point, that is squaring. You need to take the instantaneous values of current or voltage from the graph and then square it, and then you have to find the average of it or arithmetic mean of it. After that, you have to take the square root. Okay, so for that I will be drawing a circuit. Okay, I will be explaining that with the help of a circuit. So here you see, this is the graph. Okay, and here, for example, I am having current on y-axis and time along x-axis. So here, for example, let us consider this is the wave. Okay, this is the wave, a sine wave. Okay, so here you need to consider the instantaneous values. For example, I am considering like this. So here I am taking a current value I1, and here I am taking another current value I2. Here another value I3, and here I4, like that. Okay, I can take n number of values. Okay, it is not restricted here actually, so I can choose n number of values from this graph, I1, I2, I3, I4, like that. I can take many values. After taking all these things, what I have to do? I have to take the square. Okay, so square means what will happen? Here you see I1 square plus I2 square plus I3 square plus I4 square. Okay, I am considering the square, and I am actually finding out the arithmetic mean. Okay, arithmetic mean. Arithmetic mean means I have to divide this by 2, and when I take the square root of it, I will be getting the root mean square value. Here I have actually taken the average or arithmetic mean, so of the squares, and then I am taking the square root. So that is called root mean square value. And mathematically, how you can express this root mean square value? So that is very important. Here IRMS. Okay, so IRMS is equal to integral 0 to capital letter T into I squared dt divided by integral 0 to T into dt. So after doing this, I need to take the square root. Okay, square root of integral 0 to capital T I squared dt divided by integral 0 to capital T into dt. This is called RMS value or effective value of the current. Okay, for voltage also the same procedure is applicable. Okay, if you have a voltage along the y-axis instead of current, in that case you will be doing the same mathematical operation for different values of voltage. Okay, E1, E2, E3, E4, like that. Okay, you have to consider the different values of voltages, that is E1, E2, E3, and then you need to take the RMS value. Okay, it is similar. So now I will be writing the final expression for the RMS value of an AC current of the form. Okay, I equal to I naught. So I equal to I naught sin omega t. Okay, so this diagram actually. Okay, I equal to I naught sin omega t. This is a sinusoidal wave. So on this graph represents the equation I equal to I naught sin omega t. And what is your final expression for the root mean square value of current here? I equal to I naught divided by square root of 2. Okay, so this is actually the RMS value. Okay, so here actually I can write the subscript RMS. Okay, RMS, or I can write it separately for your better understanding. So what is the RMS value? I can write it as I RMS is equal to I naught divided by square root of 2. Okay, that is, you need to divide the peak value of the current by square root of 2. That will give you the RMS value. Okay, so this is how you need to find out the RMS value of current. Now instead of I equal to I naught sin omega t, if you have E equal to E naught sin omega t. Okay, so in that case what is the value of your RMS value? So first of all, let me give you the expression for mean value of alternating voltage here. So mean value of this voltage, that is represented as, so integral 0 to tau e dt, okay, whole divided by integral 0 to tau dt. This is the mean value of alternating voltage of this form, okay, E equal to E naught sin omega t. So for this, I will be writing the average value over one half cycle, okay. So I think I can better write it in another slide, okay. So your voltage is E equal to E naught sin omega t, and here what is your mean value or average value, okay, that is represented as, so this is mean value, okay. So this is integral 0 to tau e dt whole divided by integral 0 to tau dt. This is the expression for mean value. Now I will be writing the expression for RMS value. So root mean square value or RMS value, it can be written as E RMS, okay. So that is equal to E naught divided by square root of 2, okay. This expression is similar to this thing, okay. Here I RMS equal to I naught by root 2, right? So it is exactly similar to this expression. So here E RMS equal to E naught by root 2. And what is the average value over one half cycle? This is the average value for complete cycle. And what is the average value for one half cycle? So that also I will be writing here. Average value for one half cycle. So that is given by E average, okay. E average is equal to 2 E naught divided by 5, okay. Okay. So this is the average value for one half cycle. So likewise, you can find out the mean value, RMS value, or average value for any value of your alternating current, and we will be now discussing the RMS values for different signals, okay, different AC signals we will be discussing. So here for a sinusoidal wave, we have discussed the mean value, RMS value, all that, okay. And for different kinds of signals, how can we calculate the sinusoid for different kinds of signals, that is half wave rectified wave or full wave rectified wave or square or rectangular wave, how can we find out the RMS value or average value? So that we will be seeing now, okay. So now our wave is half wave rectified, okay. So half wave rectified. So half wave rectified wave means your signal will be like this. Okay, so your signal will be like this. You will be having only the positive half cycles. So this is how your signal looks like. So 0, pi, and 2 pi, okay, like that. So this is the half wave rectified wave. That means you will be getting only the positive half cycles. Here, what is the RMS value? So here, the RMS value is given by I naught by 2. Okay, I naught by 2. So that will give you 0.5 I naught. Okay, and what is the average value? Average value or mean value? So mean value is given by I naught by 5. We are not bothered about the derivation of all these things. We just have to know the values. So 0.318 I naught. This is the mean value for half wave rectified wave. Okay. And one more thing. So here I have told you IRMS equal to I naught by root 2. Okay. When you divide this I naught by root 2, you will be getting IRMS is equal to 0.707. 0.707 I naught. Okay, this is the expression. When you divide I naught by root 2, you will be getting 0.707 into I naught. Okay, this is the RMS value. So here we have discussed the RMS value and mean value for the half wave rectified wave. Now we will be discussing it for full wave rectified wave. So full wave rectified. Full wave rectified wave means, how does it look like? So here you see you will be getting the negative half cycles as the positive half cycles. Okay, I hope you can understand this, because here you see here you are having the positive half cycle and a negative half cycle and positive half cycle alternatively. In a full wave rectified cycle, this part, okay, this negative half cycle part actually gets converted into positive half cycle and appears like this. That's the only difference. Okay, in a full wave rectified circuit, what happens? This negative part, this negative half cycle actually gets converted into positive half cycle and appears like this. So that has happened here. You see, this is the positive cycle. Okay. So the negative cycle has been converted into positive half cycle. So this is the full wave rectifier or fully rectified signal. So here, what is the value of this RMS, root mean square value? So RMS value here is I naught by root 2 actually. I naught by root 2. That will be 0.707 into I naught. Okay. And similarly, what is the mean value? The mean value is given by 2 I naught divided by 5. 2 I naught divided by 5, that will be 0.637 I naught. Okay. If it is not clear, let me write it again. 0.637 into I naught. This is the mean value. And now we will be discussing these values for a square or rectangular wave and also sawtooth wave. So for these waves we will be discussing now. So this is square wave. Okay. Or you can also consider a rectangular wave. That's not an issue. So this is square or rectangular wave. Here, what is the RMS value for a square wave? RMS value is nothing but I naught. Okay. So in all these graphs, you are having current along the y-axis and time along the x-axis. You should remember that. So RMS value equal to I naught here, and average value or mean value is also I naught. Okay. So mean value is also I naught. Okay. Then we will be discussing for sawtooth wave. Okay, sawtooth wave. How does it look like? Sawtooth wave. So a sawtooth wave actually appears like this. Okay. You can easily understand from the shape of this. Okay, the sawtooth. Sawtooth usually looks like this. Okay. This is the sawtooth wave. So here, what is the RMS value? This is the sawtooth wave. And the RMS value is I naught by root 3. RMS value is I naught divided by root 3. And the peak value, or the mean value actually. This is not peak value, this is actually the mean value. So mean value is nothing but I naught by 2. Okay, I naught by 2. So these are the expressions for some of the AC signals. Okay, how can you calculate the RMS values and the mean values for different types of AC signals? I have given you the information. I hope you all can understand this. Okay. So now we will be moving on to the concept of phase. Okay, the concept of phase. So let us consider a signal I equal to I naught sine omega t plus or minus phi. Here, what is the meaning of this phi? This phi is called initial phase. Okay, so this phi is called initial phase, and instantaneous phase, how can we find out? So instantaneous phase for a signal can be found out using omega t plus or minus phi. Okay, so this initial phase is actually a constant. Okay, it does not change with time. The initial phase. The initial phase does not change with time, and this instantaneous phase can change with time. So it changes with time actually. Okay. Then what is the SI unit of this phase? It is actually radian. Okay. SI unit of phase is radian. SI unit of any phase, be it an instantaneous phase or initial phase, SI unit is actually radian, right? So this is the concept of phase, and now I will tell you what is the meaning of this phase difference. What is the meaning of phase difference? So that I will be discussing with you. For that, let us consider two signals. So voltage V equal to V naught sine omega t plus phi 1. This is the alternating voltage. Okay, V equal to V naught sine omega t plus phi 1. And for alternating current, I will be writing the expression I is equal to I naught sine within the bracket omega t plus phi 2. These are the two signals. So here, the phase difference of current with respect to voltage. Okay, the phase difference of current with respect to voltage. How we can find out? I will be telling you now. So the first thing is phase difference of current, okay, or I with respect to voltage V. So that is given by phi is equal to phi 2 minus phi 1. Okay, phi 2 minus phi 1. So here phase difference of current with respect to voltage, that is phi equal to phi 2 minus phi 1. That means with respect to which quantity? So with respect to this quantity means the phase of this quantity should come in this place, okay, after the negative sign. Here phase difference of I with respect to V, that means the phase of I should be written first, that is phi 2, and the phase of V should be written next, that is phi 1. And when you find it vice versa, okay, when you find the phase difference vice versa, that is phase difference of V with respect to I. V with respect to I. So here phi is equal to phi 1 minus phi 2. Okay, that's a difference here. Okay, both are not the same. When you want to find out the phase difference of I with respect to V, you need to use this formula. When you want to find out the phase difference of V with respect to I, you need to use this formula. Okay, both are not the same. You should be careful regarding the order of appearance of both these phases. Okay, here phi 2 minus phi 1, here phi 1 minus phi 2. Likewise, you need to consider. And now we will be discussing the concept of leading and lagging. Okay, leading and lagging concept of phase, or lagging and leading concept, because this concept will be useful for you in understanding the Phasor diagram. So please listen carefully. Lagging and leading concept of phase. Okay. So the first thing is V leads I. Okay, V leads I. Or otherwise, it can be called I lags B. Okay, I lags B. So what is the meaning of this? Voltage leading the current or current lagging behind the voltage. What is the meaning of this statement? This means, okay, here voltage is leading. That means voltage reaches maximum value before current. Okay, voltage reaches maximum value before current. Okay. So I can give you a simple example here. Okay. So you have two siblings, X and Y. Okay. X is actually 3 years elder. Okay. X is actually 3 years elder than Y. Elder than Y. Okay. So what will happen here? The academic progress of X actually leads Y. Okay, the academic life of X actually leads the academic life of Y. Okay, so if X completes his higher secondary level, okay, if X completes his higher secondary level by 2022, okay, Y will complete the higher secondary level by 2025. Higher secondary second year. Just for an example, I am telling you. Or you can also take the example in which X completes his graduation, okay, undergraduation or even higher secondary second year you can take. If X completes higher secondary graduation, higher secondary second year in 2022, then Y finishes up the higher secondary second year in 2025. Okay. So in this way, the academic progress of X leads the academic progress of Y by 3 years. So X is 3 years elder than Y, and that's why X is leading Y by 3 years. Okay. So similarly, here when we say V leads I, that means voltage reaches maximum value before current. Okay. So we can explain this with the help of equations and diagram. So V equal to V naught sine omega t plus phi. In that case, I is equal to I naught sine omega t. Okay. So if V equal to V naught sine omega t plus phi means then I equal to I naught sine omega t. Or it can also be the other way around. Okay. If V is equal to V naught sine omega t, in that case, what is the value of I? So I will be I naught sine omega t minus phi. Okay, both these equations are correct. So If V equal to V naught sin omega t plus phi and I equal to I naught sin omega t. Okay, in this case also voltage leads current by phi. Or if V equal to V naught sin omega t and I equal to I naught sin omega t minus phi, in this case also voltage leads current by the phase phi. Okay. So how can we represent this scenario with the example of with the example or with a diagram? Okay, we can explain this scenario with a diagram. So I will be drawing the diagram here. So here I am representing voltage by this thing. Okay, that is dotted line. Okay, so this is the voltage here. Okay, so this is actually V. In this case, how does your current varies here? So your current actually varies like this. Like this. Okay, this is current. So here you see this blue color dashed line represents the voltage. It reaches maximum before current. Okay, it reaches maximum before current. It starts here from the maximum. At that time, the current starts from zero. Okay, the current starts from zero, and it will be reaching the maximum. Current will reach the maximum when your voltage is minimum. Okay, so likewise it varies. I think you can understand the concept. Here you can see the blue color dashed lines. It starts from maximum. That means voltage reaches maximum before current. Okay, even before the current reaches maximum. So this means voltage leads current by phi. Okay, the phase difference. So this is the meaning of leading. Okay, voltage leading current. Okay, and we can also consider the second scenario, that is voltage lags behind current. Okay, voltage lags behind current. So voltage lags behind current or I. Or you can also call this current leads voltage. Okay, you can also call it the other way, current leads voltage. This means current reaches maximum before voltage. Okay, current reaches maximum before voltage. So here the equation changes in the opposite way. So if V equal to V naught sin omega t, in this case I is equal to I naught sin omega t plus phi. So it is exactly the opposite scenario. You can see here, if V equal to V naught sin omega t and I equal to I naught sin omega t minus phi. Here if you have minus here, voltage leads current. Okay, but here you have I naught sin omega t plus phi. This means current leads voltage. Okay, you can have the other forms as well. If V equal to V naught sine omega t minus pi, okay, omega t minus pi, then I is equal to I naught sine omega t, okay. So this scenario explains that voltage lags behind current. And how can you represent this? Here current reaches maximum before voltage. So in that case, we can draw a diagram for this. Here you see so I will be representing voltage by blue color once again. Here the voltage actually follows this pattern, okay. So this is voltage. And what about current? In this case, the current actually follows this pattern, okay. Current actually follows this pattern. Here you see the current starts from maximum. At that point, the voltage starts from 0. So current reaches maximum before voltage. Okay. So I think you can understand all these things. So here V equal to V naught sine omega t, because this is a sine wave, as you can see. Okay, V equal to V naught sine omega t, and here I is equal to I naught sine omega t plus phi. Okay. So current reaches maximum before voltage. I think you can understand all these examples. Do you all understand these concepts, students, up to this point? The concepts of phase and phase difference, do you all understand?
Yes, sir.
Anyone having any doubt? If you have any doubt, you can unmute yourself and you can ask. Okay, students, if you have any doubt, you can unmute yourself and you can ask. Okay, I think you don't have any doubt. So in that case, I will be moving on to the next concept. The next concept is Phasor and Phasor diagram. Okay, Phasor and Phasor diagram. So if you want to understand this concept, we need to consider the circle now. So initially I will be drawing a circle here. Okay. So this is one diameter. This is one more diameter. So if your equation is y equal to a sine omega t, if your equation is y equal to a sine omega t, this is the expression for simple harmonic motion. Here a is the amplitude of simple harmonic motion, and the projection of this vector capital A, okay, it is rotating with constant angular velocity omega. Okay, so here this vector I can show like this. This vector A, the amplitude vector A, I can show like this. It is rotating with angular velocity omega. Okay. So for a simple harmonic motion, this A rotates with angular velocity omega. So here this is y. Okay, this is y. This thing is actually this is y, and this vector is actually A. Okay, this arrow. This angle is omega t. So here this simple harmonic motion, the amplitude vector A rotates with angular velocity omega t. So now here what is the meaning of this A? A is actually called the phasor of y. Okay, A is called the phasor of y. Why we are calling A as the phasor of y? Okay, so let me write it here. Here A is called the phasor. A is called the phasor of y. So when you want to compare the phase, okay, of two sinusoidal quantities, then you will be needing the concept of phasors. Here you can say the quantity y, which is varying sinusoidally according to this equation, and here A is called the phasor of y. Okay. So now we will be discussing more on this phasor and also phasor diagram. Okay. So now we will be considering these equations. V equal to V naught sine omega t. Okay, and I equal to I naught sine omega t plus 1. Okay. So these are the equations. So here you see V naught is phasor of V. Okay, and I naught is phasor of I, both rotating with the same angular velocity omega. Okay, V naught is the phasor of V. I naught is the phasor of I, both rotating with common angular velocity omega. But here you need to see which one is leading. Okay, according to this equation. So V equal to V naught sine omega t and I equal to I naught sine omega t plus phi. This means current is leading the voltage by phi. So similar equation I have written here. Current is leading the voltage by this phase phi. Okay. So we have to represent the phases I naught and V naught in the phasor diagram. In the phasor diagram, I have to explain which one is leading and which one is lagging. Okay. So these things I have to explain in a diagram. That diagram is called phasor diagram. Okay. Previously we have discussed the concepts of phase difference and the leading and the lagging concepts of phase. Here we need to represent diagrammatically, okay, the leading and lagging of this phase. So V naught is one phasor and I naught is another phasor. So how one phasor is leading the another phasor, that we have to represent with the help of a diagram, and that's what I'm going to do now. So let us draw the graph. Here you have Here you have x-axis, and here you have y-axis. And here the phasor of V is V0 and phasor of I is I0. So here the phasor I0 should be ahead of V0 by angle phi. Okay. Current leads voltage. Current leads voltage. So that we have to represent here. Current leads voltage. That means the voltage is here. Okay, the voltage is here. So this is V0. And here you are having V. Okay. Now, where is your current? Where is the phasor I0? Your phasor I0 is actually here. So this is I0 and this is I. Here you see the current is actually moving forward. It is ahead of voltage. You consider that both these phasors are rotating in the anti-clockwise direction. In this case, which one will reach the maximum first? Can you tell me? In this case, which one will reach the maximum first? Current or voltage? Both are rotating in anti-clockwise direction. Can you tell me?
So voltage, sir.
No, actually here you see the current is having a lesser angle. Okay, the current is having lesser angle with the y-axis. So the current, the phasor I0 and voltage V0, both are rotating in anti-clockwise direction, but the angle made by this I0 with the y-axis is less. That means when it is rotating in the anti-clockwise direction, this I0 or this I reaches maximum initially. Okay. So this is called phase here. That phase difference is phi, and the rotation velocity is omega. This is omega t. So here you see this I0. Okay. So here both the phasors are rotating with angular velocity omega, and both are rotating in anti-clockwise direction. So in this case, this angle actually. So this angle made by this phasor I0 with the y-axis is lesser compared with the angle made by this y-axis with V0. So this angle is greater. That means this voltage has to travel this much of distance, angular distance. Okay, this V0, this phasor V0 has to travel this much of distance. Okay, it has to travel this much of distance in order to reach the maximum. But this current has to travel just this much of distance. Okay, that means it reaches maximum first. So this is why current is leading voltage by phi. Do you all understand the concept of phasor diagram now?
Yes, sir.
Anyone having any doubt? Because based on this concept of phasor diagram only, you can understand different types of AC circuit. Okay. Next class we will be discussing AC circuit containing pure resistor, pure inductor, okay, and pure capacitor. All these concepts will be discussed in our next class. But if you want to understand all these concepts, you need to understand the concepts of phasor diagram first. Then only you will be able to understand the different kinds of AC circuits. The LCR circuit and circuit having just inductor, just resistor, all these concepts can be understood only when you understand the concept of phasor diagram. Anyone having any doubt or difficulty in understanding the concept of phasor diagram, now you can tell me. Students, anyone having any doubt? You can tell me now. on phasor diagram or whatever concepts we have discussed today? Any doubt? Okay, students, in the absence of any doubts, we shall stop.
No doubt, sir.
Yes, we shall stop with this much here, and we shall discuss the remaining concepts in our next class. Thanks for joining the session.
Thanks, sir.